Welcome back, AP. Last section of Chapter 3, 3.7, Limiting Reagents. Okay, this is a very important topic because it determines who stops the reaction. So between your reactants. Let me give you like a little analogy. You ever notice hot dogs versus the buns? The packages of the buns, there's actually 10 buns. But the hot dogs, there's actually 8 of them. So, which means if you had 10 and 10, you could make 10 complete hot dogs with the buns. But the problem is your hot dogs, you actually run out first. So that means you have 2 leftover buns that kind of wasted, just not used. So the problem is, if you have leftover, that means that's not part of the reaction. It's left over. And we like to call that excess. The reactant that runs out first is our limiting. So the limiting reagent, and it's a reagent, a reactant. So we're talking about the reactant side, is the one that gets consumed first. So when we're solving these type of problems, we have to figure out which reactant is used up first. And once we know who was consumed first, we convert all the products. And then when we convert to the product that they want us to solve for, that's how we know who's going to stop the reaction. Okay, because that means theoretically you can only produce that much product. So the limiting reactant will determine, theoretically, we like to call this theoretical yield, basically how much product can be produced. And remember, this would be like 0 error in any type of lab experiment. On the other reactant is your excess. So if you have like an A and B scenario and make C, A, one of them has to be your limiting, and the other reactant has to be your excess. And C, your product, well, that just means however much you can produce. With your excess, after the reaction has stopped, you actually have leftover. So basically, it's like sitting at the bottom of the beaker, looks like a precipitate probably to you, or maybe it's in the weigh boat and you only had to weigh so much and you have leftover that's sitting in the weigh boat. Okay, so basically it's not part of the reaction. So the exit reactant remains because there's nothing to react with it because the limiting got used up. The reactant that produces the least amount of product is your limiting. So in other words, who stops the reaction? And that's usually the hardest part. So who stops the reaction is we got to do some math. So if you're given moles, then go to moles of one chemical to the other. If you're given grams, then go to grams. Okay? You always want to compare the same unit with the same unit. So if you're given grams of reactant 1, go to grams of reactant 2. Same thing for moles. Then we got to talk about 2 important words of need versus have. And once you figure out what you need, the question is, do you have what you need? And that will determine the limiting. So let me show you step by step on how to do one of these scenarios before we look at like some particle diagrams. So let's say I have this equation, sulfur reacts with chlorine gas, and I get SCl6, and it looks like my equation is balanced, so that's good. I have 202 grams of sulfur, and it's allowed to react with 303 grams of chlorine. Which is the limiting? Well, I don't even know which one. Who do I start with? So usually my rule of thumb is I like to start with the first one. I don't know why, but I always start with the first one. So right here, if you're given grams of reactant 1, go to grams of reactant 2. So I'm going to take these grams and figure out how many grams of this chlorine do I need? Okay, because remember, this right here, this is what I have. But what do I only need to make the reaction go to completion? So I'm going to start with this 202 grams of sulfur, and these are 3 steps. When you go grams to grams, this is 3 steps. If it was mole to moles, then you would just be doing 1 step. But remember, we're going to need the balanced equation because we need the coefficients to change the chemical. So I'm going to start with sulfur, and I already know I'm going to go 3 steps. So I need my periodic table. Sulfur, periodic table, mass says 32.06 grams for every 1 mole. So now remember, this is when mole ratio comes in. Look at your balanced equation. For every 1 mole of sulfur, so I got rid of my grams, and now I'm getting ready for sulfur. And I want to compare the other reactant, diatomic chlorine. My coefficient says 3, so I'm going to put a 3 on top. So now let's get rid of moles. For every 1 mole of diatomic chlorine, 2 chlorines, I have a diatomic mass of 70.9. Remember, for diatomics, we don't need to show molar mass chlorine times 2. So we're going to multiply 202 times 3 times 79, and then we're going to divide by 32. So when you plug this in, let's get those calculators. It looks like we're going to get 3 sig figs, so you should get 1,340 grams. Now let's talk about what these 2 words need versus have. So in the beginning of the story, you were given 303. That's what I have. But the question is, am I going to use all of that 303? So notice right here, to make the reaction go to completion, this is what I need for that reaction to go to completion. Which means if I wanted to use him all up, I would need 1340. I have 303, but I need 1340. I don't have what I need. I'm short. So that means my chlorine stops the reactants, stops the reaction. So he's my limiting. He stops the reaction. Could I have started with chlorine and then go this way to sulfur? Absolutely. You're still going to get the same answer. So that means my sulfur, I have too much. So this excess, I'm going to have left over. So the other part of it is that 202 didn't get all used up. So there's going to be some leftover. How much leftover? Well, I'd have to do some math for that. So this is the question that you always ask yourself. Do you have what you need? And if you have what you need, then chlorine would have been the excess and sulfur the limiting. Okay? So continuing this scenario, how much product will be produced? Well, now that you know who the limiting reactant is, which in our case was chlorine, every reaction, every calculation, you have to start with the limiting and then calculate to whatever you're trying to solve for. The reason why is because, remember, the limiting reactant was all used up. You have no leftovers. So he is going to determine how much product you can only produce. Okay, so theoretically, we call that theoretical yield. That is how much you can only produce. So I'm going to start with my chlorine. And remember, you're starting with what you have. So for chlorine, I have 303 grams because that's what I have. So with my limiting starting, for my chlorine, I'm going to start with what I have. So 303 grams of chlorine. And my product, according to my balanced equation, is this SCl6. So my product, I'm just making myself a note, SCl6. So grams, get rid of the grams of chlorine, 1 mole. And remember, this is diatomic chlorine, so 70.90. Bye-bye grams. And now we're going to get rid of chlorine and get to that product, SCl6. So according to my equation, I have 3 Cl2s for every 1 product. So this is only when you look at those coefficients, not during the mass. So bye-bye chlorine, and because I need mass, I'm going to need to do molar mass of that SCl6. So grams on top, and let's show a little molar mass to the side. So sulfur, 32.06, and then my chlorine, I have 6 times that chlorine. So according to my calculation, let's get chlorine, 35.45 times 6. So because I need to keep that 2 after the decimal, 70. So I just took chlorine times 6, and I'm going to add that up, 32.06, and my molar mass, 244.76 grams of SCl6. And I'm going to put that on top and 1 mole on the bottom. So bye-bye mole. So we are going to multiply the 2 numbers on top, but I actually have to divide twice. So divide 79 and then divide by 3. So let's plug this in, and if we do this right, we should get that blue number that's listed. So 244.76 times 303, and then divide 790, and then divide by 3. So ladies and gentlemen, it's not so much that you're copying down the work that I'm showing you, but you got to make sure you know how to work your calculator. Okay, so in my calculator, I got 348.6, but because of 3 sig figs, 349, and then grams of SCl6. If you're not getting this answer, then you need to ask me in class so I can see how you're plugging it in to the calculator. So that is for solving for one of the things that they asked for. Now, part C, what mass of the excess reactant is left over? I need to know, well, first of all, who is the excess? Well, sulfur is the excess. So how much sulfur was actually left over? So in the end, I need to figure out grams of sulfur, but who do I start with? Well, you always start with your limiting reactant. 303 grams of chlorine, and I need to figure out how much do I need of sulfur. But remember the equation, I had 202. I didn't use all that 202. So right there, 202 didn't get used up. So how much is left over of that 202? So basically, it's this equation, 3 steps. And the cool part is, you already did it up here, but it's backwards. So because we started with sulfur, we went to chlorine. Well, now we got to go chlorine and work our way to sulfur. So we have everything we need right up there. So I'm going to put my 70.9 grams of chlorine and my 1 mole of chlorine on top. Grams are gone. Chlorine, according to my balance equation, 3 moles of chlorine. And on top for sulfur, I'm going to go back and check my equation. So for sulfur, for every 1, there's 3 of chlorine. So bye-bye chlorine. And now my periodic table, 32.06 grams of sulfur. And we're going to plug that in. So we're going to take the 2 top numbers, 303 times 32.06. So I like to keep track of what I'm plugging in the calculator, and then I'm going to divide by those 2. So divide 70.9 and then divide 3. So according to this problem, I only needed 45. It looks like we're using 3 sig figs, so 45.7. All right, so now that we know what we need, so what is actually left over? So let's look back at the story. So we were given 202 grams. So remember, that's what you have. So what you have is 202 grams of sulfur, but I only need to make this reaction complete 45.7 grams. So what is left over Well, I'm going to subtract. So here's where you can get a little bit of trouble, is the sig figs. Because 202 has nothing after the decimal, and this one does, I need to make sure I have nothing after the decimal. So my calculator tells me 156.3, so I'm going to say 156 grams of sulfur. Okay, so let's make sure we always box our answers, and that's how you figure out limiting versus excess. I have a couple other scenarios, so that way you can see the differences. This is an actual AP exam question back from 2018, where they actually used particle diagrams instead of stoichiometry. So it says a student investigates the reaction of nitrogen oxides. One of the reaction in the investigation requires an equal molar mixture of NO and NO2. So as you see right here, equal molar, I have 2 moles of each one. That's what they mean by that, which a student prepares by using the reaction above. The particle level representation of the NO and NO2 in the flask at the completion of the reaction is NO and O2 shown in the box on the right. So this right here, in the flask of depletion between NO and NO2 in the box to the right. In the box below on the left, draw the particle level representation of the reactants. So this is going to be our reactants, and this is our, I'm going to say end of reaction. I'm not going to say the word products. Oops, reaction. And you can abbreviate the word reaction. Draw the particle level representation of NO and O2 that would yield the product mixture shown on the right. So let's look at what's first in the right. So it says these open circles are oxygen, so I'm just going to label it. And these darker ones are nitrogen. So that right there, that's NO. And I have another NO right there. And I have another NO, and I have another NO. So I have 4 NOs sitting over here. These other particles right here, well, that's the nitrogen, and that's an O, and that's an O. Well, look right there, that's my product. So my product, I have NO2, but I also, and I'm going to circle those so I can keep track. So I also have 4 of those. So in my particle diagram, I have 4 NO2s, and I have 4 of the reactant. So in order for me to have 4 of them, well, what does my equation show me? I have NO and O2 and NO2. And according to my balance equation, I have to have equal moles 2 and 2. Okay? So, what are the scenarios for me to have 4 and 4? So if I actually produced 4 moles of NO, and I have 4 moles of NO2, then what about my O2? Well, because it's a 2 to 1 to 2 ratio, that means I'm going to have a 2 times 2 is 4. So that means 1 times 2 and 2 O2s. And then 2 times 2 is the 4. So for me to produce 4 NO2s, but I still have, here's the problem that's troubling. I have 4 NOs left over. So that's why I said end of reaction. So that means I have 4 NOs that were excess, that did not get used. So what's going to lead me to a scenario where I have 4 NO2s and I still have 4 NOs left over? So what if I times it by 2 again? 4 times 2 is 8 NO. And then another 2 is 4. Well, for this reaction to have no limiting or excess, I would have to produce this, NO2. And I don't have that many. I have only this. This is all I produced. So the question is, what was in the beginning for me to have 4 left over. So for me to have 4 NO2s, I had to have had 2 O2s. So in my drawing, and I can't color in the white, I must have had 2 diatomic oxygens to begin with. But then how much NO did I have to have 4 left over? Because I have to produce the same amount of NO with the same amount of NO2 and have 4 left over. So how many NOs did I have in this reaction? Well, I must have had 8, because right here 4 of them got used, and that means I had 4 left over in my picture. So in my reactant side, I would be drawing, coloring them in, a nitrogen with an oxygen, but 8 of them, because 8 NOs plus 2 O2s. All of my O2 got used up, and how do I know? Because there's no O2s in my product mixture. And I have 4 NOs left over, so that must mean I had 8 to begin with because I have 4 left over. The key part to this was they said you had to have equal molar mixture of NO and NO2. So I could only produce NO2, 4 of them, which means I had to have 4 NOs to react with. So in this picture right here, oops, I don't know where it went. Where my circle went. All right, so I'm going to have my black circle with a white one, and I'm going to draw 8 of these. When you're drawing gases, because remember this reaction was gases, you have to make gases behave like gases, which are homogeneous. They are completely spread out. You don't want to make it look like it's heterogeneous. All the one gases on one side and the other gas on the other side. So I have 1, 2, 3, 4, 5, 6. So let's draw like another one, maybe one up here. Oops, try to keep them all the same size. Bad circle right there. There you go. A little bit bigger. And maybe one about right there. And there you go. Okay. Let's try another one, because I know you guys can plug and chug, but can you do it with a particle diagram? So with particle diagrams, they're used to represent the reactants and the products. Here's another type of scenario where I have the most famous water equation, and the way the structure looks, these look like they're gases. If that water would have been a liquid, then the liquid would have been just sitting, those molecules would have been sitting down at the bottom. So notice right here, I have equal amounts of H2 and water. So right here, my H2 are these white ones, these diatomic. These red ones are the oxygen. And how do I know? Because according to the periodic table, oxygen is bigger in size than hydrogen. Okay, remember, oxygen has 8 protons, whereas hydrogen only has 1 proton. Okay, so right here, I have in my picture what they drew. I have 2 O2s for every 4 H2, as you count right there. So that must mean 4 waters. Because everything was used, you have no limiting, and you have no excess. Because if you had excess, you would have another chemical, water, or hydrogen, or O2, you would have another chemical inside this final mixture. But we don't. Okay? So this reaction is what we call goes to completion. I have no limiting, and I have no excess. Well, let's see if this scenario is the same thing. So, for every 2 hydrogen, so right here, I need 1 oxygen. So if you notice right there, for every 2 hydrogen, I need an oxygen. Okay? And same thing here. Remember, these are O2. For every 1 O2, I need an oxygen. So far, I'm going to produce 1 water. So when we draw water, oxygen is in the center. So far I got 2 waters that I produced. And my hydrogens, they look like little Mickey Mouse ears. And right here, because it's 2 to 2, I actually have even more water that I produced. So I'm going to put another water and another water. Okay, because remember, these two are in equal proportions. So if I have those 2 right there, okay, then I need to have 2 waters. So this right here will get me 2 waters, and this reaction will get me 2 waters. Okay, so I'm going to draw my 2 waters right there. And then I have this scenario, and that's going to get me another 2 waters. I'm just going to space my waters out. Maybe draw another one up there. But now look right here. I have an O2 that's not being reacted with. He's got nobody to react with. He's got no hydrogen. So that must mean that I ran out of who? I ran out of hydrogen. So that must mean if I ran out of hydrogen, I don't have any to react with this O2 because that's O2. That means my hydrogen was limiting. And then what else is in my, because remember this is the reactants, but this is the end of my reaction. Well, that must mean this diatomic oxygen is left over. So I'm going to draw my 2 red ones right there in the center. Okay? So that's how you figure out using particle diagram. You need to make sure if your reactant has 2 moles and your product has 2 moles, you need to make sure that they're equal molar from one to the other. Okay? We will practice more particle diagrams in class. The last topic, theoretical, actual, and percent yield. Okay? So we've already talked a little bit about theoretical yield, and you can abbreviate it TY. Actual, and then percent yield. So theoretically, no errors in the lab. That's what you should produce at the end of the experiment. But what do you actually produce is called, obviously, your actual yield. So what we like to do is we like to compare how good your data is. And we call it percent yield. So percent yield compares your actual to your theoretical. So in life, we would all love 100%. Just like on a test, we would all love 100%. But it's really impossible. Why? Because errors happen in the lab. So the maximum percent is 100. But you can't get over 100. And why? Because you can't create matter. You either have 100 or you have less than 100. So with our percent yield, you will not always make all of what you're supposed to. And because of why? There's errors in lab techniques. You can't blame equipment. Okay? There's always human error. And we're trying to limit that error. Experimental, aka actual, that's how much you actually made. Now you can only determine this by weighing out your final product. So you determine this in the lab after the reaction. Okay? So actual, and you can abbreviate it AY. Theoretically, if life was perfect, no screws up or errors, then you have theoretical. So actual over theoretical times 100. Usually we would have grams divided by grams because we're weighing it out. Theoretically, you have to calculate. You have to calculate this. Actual is you weigh it out in the lab. So our grams will cancel with grams and we will get that percent. The higher the percent, oops, the better the data. So high percentage is good, okay? So usually in lab, we would like to have at least 85 to 90% yield, but we all know things happen. So let's practice this, okay? I have methane, 32 grams of methane. The formula for methane, we talked about in chapter 2, CH4, is burned in a combustion. Well, that just told me a lot. Combustion reacts with O2, and methane's a gas, combustion. And it says 30 grams of water are experimentally produced. Well, with combustion, we always know we're going to get water and CO2 gas. And quick little balancing, I would need a 2 on water, and I would need a 2 on my O2. What is my percent yield? Okay, well, first, percent yield, I need to know actual over theoretical times 100. So I have my equation. I always need an equation. Experimentally produced, well, that just told me right there that's what I actually produced of water. So here's the question. Theoretically, what was I supposed to produce for water? I got 30 grams, but theoretically means I probably should have got more than 30 grams. Okay, because remember, this number on top will always be a smaller number, and the number on the bottom theoretically will always be a higher number because you can't get over 100%. So I need to start with my methane and figure out how much should I have produced with water. Grams to grams, changing the chemical, looks like 3 steps. There's 32.00 grams of methane, and we're going to set up our 3 steps. Now, we do need the molar mass of CH4, so carbon, 12.01. Hydrogen, there's 4 of them. And according to hydrogen, which is 1.008 times 4, so 4.032. And we're going to add that, but with good sig figs, so only 2 after the decimal, 60.04 grams of that methane. So I'm going to put that at the bottom, 1 mole on top. Grams are gone, so now it's time to look at my equation. For every 1 mole of methane, I have 2 moles, because I need to look at that coefficient, 2 moles of water. Bye-bye methane. And now the molar mass of water, which hopefully we know, 18.02 grams. So I'm going to multiply on top and divide by that 16. So remember, this answer should be bigger, larger than that 30 grams of water, because we produced 30 grams, but what should we have actually produced? So divide 16. Ooh, not good data. We should have got 71, and it looks like, what do we do? 4 sig figs, 90 grams of water. Ooh, not good. I wonder if you had Alex in your group. Maybe a little Kevin in there too. I don't know. Probably one of the 2. So actual 30 grams, and you don't have to list the equation again. You just have to list it once. So 30 grams of water, and you should have got 70.9 grams. Grams to grams times 100. So this is not looking good data. And in college, and also in AP, you would be deducted points from your data if you don't get within that 85 to 90% yield. So looks like 4 sig figs. Remember, this times 100 is just moving the decimal twice. 41.72%. This is not good data. Not good, not good. All right, let me show you another scenario too. What if, oh, let me go back on that blue one just to make sure. Yep, we got that blue answer right there. All right, so just checking. Number 5, the reaction of the combustion of octane. Well, remember, octane means 8 carbons. So C8, you take the carbon times 2, add 2. So we have 18, and it says combustion, and then CO2 and water. I'm assuming water's a liquid unless they tell me otherwise. You know we're going to need a balanced equation, so let's go ahead and get this balanced. So 8 carbons, hydrogen 18, and then 2 over here, so I'm going to need, looks like 9. And then my oxygens, I have 16 right here plus the 9. So 16 plus 9 is 25. So I'm going to put 25 over 2. Now remember, if you have to use oxygen, even though it's in the fraction, you can get it out by multiplying everything by 2. So this would be a coefficient of 2, 25, 16, and then 18. Either one is fine. You just don't have to write both equations. It says I actually produced 84.3% yield. So I actually know my percent yield. It's pretty good yield. How many grams of water would you actually expect if 95 grams were actually burned of octane? So it wants us to get to water, and we're starting with that 95 grams of octane. Well, I got to get to water eventually. So I need to figure out, if I start with 95.0 grams, how much of water should I have produced? So I need to figure out, theoretically, if I start with 95, what should I have produced of water? So in this case, we're not even looking at oxygen, so there's no point to even deal with that fraction. So 95.0 grams of octane. And 3 steps, if you haven't guessed it. We do need a molar mass. So I got 8 carbons. I have 18 hydrogens. So for carbon, let's get that calculator. 12.01 times 8. So I'm going to get 96.08 grams. And hydrogen times 18. So 18.114. We're going to keep 2 after the decimal. So in the end, 114.94 grams of that C8H18. So we're going to put that at the bottom. And 1 mole on top. And now let's get rid of the chemical. According to my equation, I have for every 1 mole of C8H18, I have 9 moles of water. And just like the one before, molar mass of water, 18.02. Okay? All right, so we're going to multiply on top, divide by 114. And once we do that, we should get, theoretically, 134.9 grams of water. Now remember, I'm going to box this. Theoretically, that's what I should produce. Always label what the heck you just solved for, okay? But it wants to know, actually, what did you produce? So it helps to write the equation. Percent yield is actual over theoretical. But what students forget is we actually have the answer, and we know theoretical, I should have got 134.9 grams. So I'm going to call that X. But you forgot part of the equation. It's also times 100. Okay? So, when you're multiplying, okay, or rearranging the equation, okay, you are going to what's called cross multiply. Okay? So this 84.3, okay, so when you rearrange the equation to get stuff to the other side, you do the opposite. I need to divide by 100, but I'm going to divide by both sides. So that way that 100's gone. And I need to multiply each side, and that's a multiplication sign right there, since I got so many X's here. 134.9 grams, but I have to do that to both sides. Actually, I'm going to put in parentheses. That way all those little dots don't get confusing. That's what's called cross multiply. So I'm going to take the 134 times 84, and I'm going to divide by 100. So 134.9 times 84.3 divide 100. Now, actually, this number should be smaller than your theoretical. So you should not get higher than 134, and we don't. So my actual yield, for me to get 84% in the lab, I need to actually produce 113, actually it's 113.7. So with 3 sig figs, because that 84.3 is dictating the sig figs, I need to produce 114 grams of water to get that 84.3%. Okay? So that's how you use stoichiometry with percent yield. So the last problem, we're going to tie in limiting with stoichiometry with percent yield. Okay, last problem. Let's say I have 35.6 grams of zinc and 100 grams of iron sulfate. Who's the limiting? Who's the excess? So remember, number one, start with any reactant and convert to the other reactant. And you know Rodriguez likes to start with the first one, okay? So these two values that they gave you, it always helps to list, this is what you have. So the question is, what do you need? So when you go from reactant to one reactant to the other, you're basically solving for, what do you need from this reaction? So I'm going to start with my zinc, my 35.60 grams of zinc. And I'm going to go grams to grams, so 3 steps. So for zinc on the periodic table, 65.38 grams, 1 mole. Always cross out those units. According to my equation, I have 3 moles of zinc for every 1 mole of that Fe2 parentheses SO4 parentheses 3. And divide by zinc. And now, unfortunately, I'm going to need to do some molar mass. So let's take a little moment over here. I have 2 irons, which my periodic table says 55.85 times 2. So I'm going to get 111.7, but I need that 0 because of sig figs. For sulfur, I have 3 sulfurs. So 32.06 times 3, so I get 96.8. And then oxygen, it looks like I have 12 oxygens, so 16 times 12. Now on the calculator, ladies and gentlemen, it says 192, but you need those sig figs. So we're going to add it up. And we're plugging and chugging. This is a big mamma jamma. All right, 399.78 grams of Fe2 SO4 parentheses 3. And we're going to put that molar mass on top. So we're going to multiply that 35.6 times 398. And then we're going to divide 65. And then don't forget, we have a number at the bottom. We're going to divide by 3. So, because I'm out of room, anytime you're out of room, you just put it down at the bottom. And I have, looks like 4 sig figs, 72.56 grams of this Fe2 SO4 3. So now, this is when you got to compare step number 2. Need versus have. And that's what I'm comparing, is that Fe2SO4, that's what I have is 100 grams. But what is this value that you just solved for? Well, that's what I need. I need 72 to react completely with 35. So to react completely. Because if it reacts completely, you have no limiting and you have no excess. But I was given 100, but I only need 72. I have more Fe2SO4 than needed. So here's the question. Who's the limiting? Okay. You're limiting your zinc ran out. And you don't have to show that. What you just showed in this calculation is that you have too much of this Fe2SO4 so that is your excess. You don't have to show why that's the limiting. You have to just prove that one of them is the limiting and one of them is the excess. Okay, it'd be overkill showing it. If you actually would have started with the Fe2SO4 and go to this one, then you would have saw that zinc is also the limiting. Okay, so this zinc, I'm going to highlight it in a different color. This number is going to be very important because step number 3, you always start calculations with your limiting of what you have. Okay, so that 35.6, I will be starting with that eventually. So question number 2 says, how many grams of zinc are left over? Well, how many are left over? Well, none. Why? It's because you used all the zinc up in the reaction. It got used up. You have none left over. All right, well, makes sense. If it would have asked me how many of this iron sulfate would I have left over, well, then I'd have to do a calculation. So that's why you see 0 grams. So used all up the zinc, used all the zinc up in the reaction since it is the limiting reagent. And AP knows what LR means. Okay. Now these next two, I want you to try yourself. How many grams of iron 3 sulfate, okay, will be left over? So here's your thought process. I was given 100 grams of that iron 3 sulfate. But what did I need? So what did I only need? And then what is left over? Okay, so I'll leave that one to you. Check your answers as you go. And then theoretically, how many grams of iron should I have produced? Well, iron is a product. So you're going to start with your limiting. And remember, our limiting was zinc. And I'm going to start with what I was given, that 35.60 grams. And I want to figure out how many grams of iron. Grams to grams, I'm sure you could figure out how many steps. See you on the next video, which will be chapter 4.